60,000 years ago. The lecture was organized within the framework of the project of the Russian Science Foundation, Extreme Space Weather, Environmental Impact Assessment. The lecture will be delivered by Professor Thomas Peter. He is from Eidgenössische Technische Hochschule Zurich, in English, Swiss Federal Institute of Technology, Zurich. This institute has constantly ranked among the top universities in the world. Professor Peter belongs to Institute for Atmospheric and Climate Science, Department of Environmental System Science. Since 1999, Thomas Peter is the professor for atmospheric chemistry. Professor was the supervisor of more than 70 PhD students and postdocs. And 15 among them have been appointed as professors. If I list all the merits and duties of Professor Peter, it will take all the time scheduled for the lecture. However, more facts. Publications, more than 300. Total citing, more than 13,000. Hirsch index, more than 60. This lecture will reflect the results published in Science this year, in 2021. So usually we pronounce the floor to you, but now Zoom to you, Professor Peter, please.
Thank you very much for the kind introduction, Professor Zizek, or Vladimir. Thanks a lot. Thanks to Irina Mironova also for inviting me here. And this is a strange world, right? Many of you I only see as black boxes. Maybe we can for a moment challenge Zoom and you switch all on your cameras. And then it would be great if some person took a screenshot and sent this to me afterwards. That would be fantastic. Now, when you said 70 PhD students in the past, then I'm afraid that Timofey and Arseny, who are also here with us, at that moment thought, well, now I understand why this guy has so little time, typically. Okay, so I will start sharing my screen. Can you actually all hear me well?
Yes.
Okay, very good. Share my screen. And this is my calendar. Let's see. Okay. Do you see this now in presentation mode?
Mm-hmm.
Very good. Okay. So, as Vladimir said, a global environmental crisis 42,000 years ago. This is a paper which was led by Alan Cooper and Chris Turney and appeared in February in Science. Amongst the co-authors, there is also Julien Annet, who used to be a PhD student with us, Eugen Rosanov from the PMOD in Davos, Marina Friedl, who is presently a PhD student, Ivo Sutter, he was a master's student, and special thanks also go to Pavle Arsenovic, also a former PhD student who helped me preparing this talk in certain aspects. And as Vladimir said, this seminar is held in the framework of the project Extreme Phenomena of Space Weather, Assessment of Impact on the Environment. Now, we had quite a number of years ago, I think 5 or 6 years ago, published a paper in Climate of the Past on the topic of the magnetic reversal of the Earth magnetic field. And we were then, just a year ago, approached by the first co-authors, leading authors of this paper, whether with our model we could help them explain some of their new findings. And this is related to an interesting discovery when in New Zealand they wanted to build a power plant, and they cleared the ground and they got out a 42,000-year-old kauri tree, which now helps to unravel Earth magnetic, last magnetic flip. So when the Earth magnetic field was close to zero and then flipped and then came back again. And this is what I will tell you about now. The problem that I myself have here at this point is that the topic is very, very broad. It goes from paleoclimate to isotope science to how a plant grows and so on. And so I had a fun time actually preparing this presentation. So this study, as has been commented by a reporter at Science, nails in fine detail the timing and magnitude of the magnetic swap. It convinces some paleoscientists as making a credible case this flip could affect global climate. And it made other paleoclimate scientists being highly skeptical of the paper. And so the paper received actually also quite some critical voices. And in particular about the paper's broader claims, given the little other evidence of a global climate crisis at that time. So what I will do is I will, instead of looking at this tree, where probably most of you as physicists have as little understanding of as I, rather start with looking at the large-scale picture and at what our sun is doing with the Earth and how the Earth is protecting itself against radiation. So there might be galactic cosmic rays coming in, for example, an energetic 10 GeV proton. And this might travel through the solar magnetic field and then also pass the Earth magnetic field and hit the ground. And on the way there in the atmosphere might undertake a few other actions that I will come to in a moment. There might also be fast protons coming from the sun, for example, a 1 GeV proton, or a slower particle, like a slower proton, which then gets caught in the Van Allen belts, for example, a 100 MeV proton. So there are various protection mechanisms that shield the Earth against these influences. There is first the frozen-in solar magnetic field, which is dragged out by the solar wind all the way from the sun to 100 astronomical units out into space. And this on the way of those galactic cosmic rays, the solar wind deflects and decelerates the galactic cosmic rays. The second protection is the Earth magnetic field, which shields the solar energetic particles, shields the Earth against solar energetic particles and cosmic rays. And last but not least, protection number 3, the Earth atmosphere itself, which has a stopping power which suffices to stop protons up to something like 2 GeV. Let's start with the first, the solar magnetic field. That is complicated. If we think of that first as a normal stab magnet, then we easily see, because it's spinning, that it takes away the magnetic field and makes it looking anything else but a stab magnet. So the field lines are complex and give rise to solar flares and so on, and also pave the way for solar mass ejections. If you then look a bit further out, and I must admit, I had never seen this plot before. Fascinating, the Parker spiral. So because the Earth is, the Sun is rotating about once every 25 days, the magnetic field is then also rotating, and it makes a spiral. So that galactic cosmic rays have to travel through this magnetic field. So we see here Mercury, Venus, Earth, Mars, Jupiter, and on the way traveling there, through this complex field, it follows curved paths. It emits synchrotron radiation or Magnetobremsstrahlung, and this will slow them down. So that is one important protection. There is clear evidence for the solar protections. The cosmic rays and the sunspot numbers are very, very strongly anti-correlated. And actually in your country, in Russia, a lot of measurements are being made in this respect. There are balloon-borne Geiger counters whose measurements are shown here from the late 1950s all the way to something like 2007 or so, which measured in the lower stratosphere above Murmansk at high latitudes and Moscow at lower latitudes, with Geiger counters, the counts, and this is here normalized relative to 100 in 1965. This is from a paper by Mironova et al. In 2015. And you very, very nicely up here, you see the sunspot number observations, and you see how nicely these are anti-correlated. This is not only happening like this at high altitude, so in the lower stratosphere, but also on the ground. This is McMurdo Station in Antarctica, Newton counters showing a very, very similar pattern. And Ilya Usorskin, who is also here in the audience, has looked into fine details of this. And for example, one now understands why every second of these peaks here is flatter. So there's a certain 22-year periodicity, and every other one is sharp. And this is visible as well in the Newton counter measurements over Antarctica. Protection number 2, the Earth magnetic field. So there are the Earth radiation belts, and let me see that I can switch on. How do I do this now? Arrow options. Okay. Like this, yes. So this shows the Earth Van Allen radiation belts in a time late in 2003 in October, and at the end of October, so pretty much now, you see how suddenly the radiation blooms. This was during the Halloween solar storms, a series of flares and coronal mass ejections in late October 2003. Let me stop this. If we look at what the Van Allen belts are doing with particles. These are particle trajectories that have been started from the Earth. I'm not quite sure, somewhere probably in the troposphere, and then following them back with different energies, and the most energetic ones take one bend and then go out into free space, while the slower ones circle around and basically are caught here within the Van Allen belts and can make loops getting stuck in the Van Allen belt. So the Van Allen belts are basically a magnetospheric protection against the outside world. On the other hand, they are filled with charged particles and therefore also a hazard for space travel. How steady is this field? How good is this protection? How reliable? This shows the view back into Earth's history, 5 million years. And everywhere where this shows a black bar, the Earth magnetic field has the direction that it has nowadays, and where it's white, it's in opposite direction, if we think of it as a simple dipole. Obviously, the polarity changed in the past, and this has been used by the geologists to also come up with their aging of the Earth, so the geological ages. If you now look at the last 900,000 years shown here, then we see that this is interrupted a few times by very short periods, which are just 1,000 years or a few hundred years long, where there was a sudden flip in the magnetic polarity, so a turnaround of the field, and that happened a few times. And the last time is the last clear turnaround is the La Chambre event. This is named after a village, the village La Chambre in southern France. You see here a photograph with the Puy de Dôme, a volcano that is close by, and volcanoes of that sort 40,000 years ago, when the lava flows became cold, they fixed the magnetic orientation, and this has been discovered in the late 1960s. And since then, this is called the La Chambre event. Now, the polarity during these flips is anything like having a stat magnet which turns from north to south and then turns once around, but it's quite complicated. So that is also what one gets out of the sedimentation archives. There have been probably a number of north poles and south poles, and the magnetic field also was not zero. It was some low value, and there were lots of locations on the planet where it was close to zero, but overall it remained finite. If these two protection measures do not hold and particles get through, the last thing that remains is the Earth itself. Now, the Earth has a stopping power, so that means particles penetrating into it, for example, here protons with a certain energy in MeV shown down here, make it, this here shows the penetration depth. And the faster they come in, the deeper down in the atmosphere they get. And they need something like about 2 GeV or so to actually reach the ground. The spectrum of these particles is shown here for solar cosmic rays and for galactic cosmic rays. And the galactic cosmic rays, this is in the vicinity of the Earth here. The galactic cosmic rays arriving there. Here you see already the strong activity, strong sun and weak sun difference So this makes the number of galactic cosmic rays in this energy range go down by almost an order of magnitude. This spans many, many orders of magnitude here. Another figure from one of the papers by Irina Mironova and colleagues is this nice figure here, showing how X-rays, auroral electrons, radiation belt electrons, solar protons, and eventually galactic cosmic rays make it down into the atmosphere. And as you see, well, that's the reason why we also can measure the galactic cosmic rays on the ground. They make it all the way through the troposphere down onto the surface. These cosmic rays leave isotopic fingerprints, and that's shown here. So nuclear reactions of cosmic ray particles with atmospheric nitrogen and oxygen, where neutrons or protons bump into, for example, a nitrogen nucleus and then form a carbon-14 isotope, or carbon-14 nucleus. And this invites to study the Greenland ice cores and the Antarctic ice cores, as well as sedimentary and volcanic deposits to reveal their information about the geomagnetic excursions. These cosmic rays can not only form carbon-14, but also beryllium-10. And in many projects that I have been in together with Eugene Rozanov and Timofey Sokodolov, looked into these problems, and presently Arseny Karagodin is doing similar work. Let's look at this a bit more in detail. Terrestrial C14 and beryllium-10 production and fate. So what happens is a cosmic ray proton comes into the atmosphere, smashes into a nucleus, for example, a nitrogen nucleus, that decays into many fragments. One of them can be a medium energy neutron that itself hits an N14, a nitrogen nucleus, forming the carbon-14, and then the carbon-14 very, very quickly recombines with O2 to give CO2. So, but this is then, of course, carbon-14 CO2. This can be taken up by plants, and since it has a lifetime, this carbon-14 of roughly 6,000 years, you can follow, after such a plant has been buried, every 6,000 years, the halving of the radiation of the radioactive decay. So the physics behind that, it starts with an intermediate neutron, something like slower than 20 MeV, bumps into this N14, makes the carbon-14, and the carbon-14 then decays by releasing an electron and a neutrino after those roughly 6,000 years. That's very similar for beryllium-10 production. What is different is the fate of beryllium-10 and its lifetime. The fate is that it loves to stick to aerosol particles. These aerosol particles then go into clouds. They can snow out, for example, onto Antarctica. And then on Antarctica, we can see the beryllium-10 distribution in the ice cores. And there again, we see here around 42,000 years ago, a clear anomaly. So very, very similar behavior. First, this fast neutron now makes the N14 nucleus being cracked up into even more particles, so an alpha particle leaving. And the beryllium-10 then, after long lifetime, 1.4 million years, decays into boron. And this can be followed. So on these time scales here, 40,000 years, not much is happening. So this means what we measure here in terms of beryllium-10 is basically a fingerprint of what happened back then, really, without much decay. So this can be used as an indicator for how frequent is beryllium-10 actually formed. So the method is radiocarbon dating. Basically, as long as the plant is alive, the carbon-14 content is the same as that of air, besides some fractionation processes. Once the tree then dies, the carbon-14 goes down. And one can follow that an exponential decay law. That sounds very nice. It would all be extremely simple if only the carbon-14 content was constant, but that is not the case. So this requires calibration, and that has been done since Libby in the 1960s, I think, by many, many people, looking at how does the calendar age over the carbon-14 age change with time? And as you see here, there is clearly a deviation. So the carbon-14 time is up to 5,000 years younger than the calendar age due to various processes. Once one knows that, one can then apply this to tree-ring radiocarbon dating. So one can take that ancient kauri tree, which was preserved in northern New Zealand wetland. Each ring preserves the record of atmospheric C14 of exactly 1 year, which it grew in, and that delivers the first continuous reconstruction of atmospheric C14 across the Lachamp event. The tree that has been found grew roughly 40,000 years ago and became 1,500 years old. It looked like that, and they still today look roughly like that. What events happened about 40,002 years ago? Well, besides finding that tree, there was a dramatic expansion of the Laurentide ice shield in Canada and in the northern US over here in the North Atlantic. There were global glacial maxima in Australasia and in the Andes, for example, here. And these Andes were actually the reason for us 5 years ago when the Sutter et al. Publication was made to already do a first study on the Lachamp event. There's continent-wide aridification in Australia and megafaunal extinction, so large animals dying out in Australia, becoming extinct. There's extinction of the Neanderthals and an increase of cave art all over Europe. So far, there was lack of exact timing and duration of the geomagnetic excursions, and that has greatly limited the ability to examine its consequences. The question is, by how much can this situation be improved? And there the answer is, oh yeah, this tree helps quite a lot. So far, the New Zealanders have sold their trees for cheap money to people worldwide to put them as furniture into their living rooms, until it dawned that one can do more with them in scientific terms. But actually, the interaction between economics and science is working quite well there. The big question, of course, is all this, which I highlighted here, a coincidence, or is it a causal relation to the Lachamp event? That's a big question, and that is what most of the struggle is about. So now this is the first figure from this paper. the first detailed reconstruction of carbon-14 across the La Chambre curve A. So this shows these archives as a function of calendar years down here. Curve A shows the calibration curve for radiocarbon dating versus calendar years. So it shows the C14 years before present here, shows how this is as a function of age slowly going down. It shows this bump here, which is due to the La Chambre event. And once this calibration here is applied, one can derive the delta 14 as a function of calendar years, which is shown in B. So this is an unprecedented clear signal in C14, which very, very precisely allows to nail down when this actually happened and when this tree died. Panel C shows the magnetic record from Black Sea sediments. It suggests two minima, so a minimum here and another minimum back here, and a slow maximum in between here. Now this invites to interpret this as a magnetic field is going down, magnetic field is reaching values close to zero, magnetic field is turning around and reverse and then a bit stronger again, and then it turns around once more and therefore goes down again until it increases again. As I said before, this would be too naive. It's not that simple. The Earth magnetic field was very likely quite a bit more complex, but it might nevertheless well be that there are two minima here which form, sandwich this transition period. In D, we see the ice core records of beryllium-10, revealing a series of peaks here, and these are occasions when a lot of beryllium-10 was formed, so marking grand solar minima, when the sun was particularly weak, as marked by those black arrows here. And the black thick curve is the carbon-14 production curve derived from the delta carbon-14, and then synchronized and used to align with the beryllium-10 record. So this is indication for the minimum Earth magnetic field. And this is indication for the minimum solar activity and the solar magnetic field. What our colleagues from Australia then did was they looked a lot into synchronizing lots of other records and came up with these events happening in this time period. So there is mid-latitude climate shift, and in the southern hemisphere, but also in the northern hemisphere, there's the rapid extinction of the Laurentide ice shield. Undoubtedly, in this time, there is a strong intensification of cave art. Whether this is related to the reversed magnetic field or not is another question. To be honest with you, I look at our paper nowadays and think some of the formulations in there are very, very strong, and I would probably now make them a bit softer in order to cover my head. There is extinction of the Neanderthals, which happened at the late in this time. And there is a southern hemisphere megafaunal extinction, so lots of larger species becoming extinct in Australia. How do we model this climate and chemistry? We use the climate chemistry model SOCOL, which originally was developed by Eugene Rozanov in Davos, and there is a whole school led by him with PhD students, who he and I had together, a real pleasure, modeling with a model which basically chops the atmosphere and the ocean into lots of little cells, and so basically a climate model with vertical and horizontal exchange between these boxes. So the whole globe is chopped into these little parts. The dynamics is described by some dynamical equations. This is, of course, quite complex. They are coupled. You need to look into the boundary conditions between these boxes. SOCOL for the application in this context was run with a relatively low resolution, 128 times 48 times 39 boxes. So this is basically shown here what Europe looks like, while more state-of-the-art climate models used by the IPCC look more like that, but then typically they do not have the chemistry that we have on board. There are something like close to 60 chemical species, just as many photolysis reactions, 180 gas phase reactions, 16 heterogeneous reactions. So in each of these boxes here, this chemistry is running, and each of these boxes via the dynamics is communicating with the neighboring boxes. And like this, the climate and the chemistry are modeled simultaneously. So for the time back then, 42,000 years ago, what do we have to do? Well, first of all, we have to see where we are in general. These shows the ice ages, the sawtooth in temperature, in CO2. 40,000 years ago, we are roughly here where that yellow bar is. So it is in any case pretty cold, and there's a lot of ice, and this ice that the model was initialized is seen here. So most of northern, or a big chunk of Northern America is ice covered, and Scandinavia as well. So we ran a reference run. We ran that for 370 years under glacial conditions with a modern geomagnetic dipole moment and the solar energetic particles and the galactic cosmic rays taken from GRAC-RI, the Cosmo Ray atmospheric cascade application for cosmic ray induced ionization model by Usoskin, Kovaltsov, and Mironova. For 72 years, we continued the reference as reference, and we had another run where the Earth magnetic field was put to 0, and a third run where the magnetic field was put to 0, and a grand solar minimum was assumed. And so also the precipitating particles are not decelerated by the solar wind. They reach the atmosphere correspondingly with higher energies. The difference between this and this is in magnetic dipole moment, 8.25 times 10 to the 22 amperes meters squared. So we basically set m equal to 0 in this case down here, and this value here is the reference case value. And the solar modulation potential came down from 800 megavolts to 0. First, look at what that means for galactic cosmic rays simulated by GRAC-RI. Here the reference run, present day geomagnetic dipole moment and solar modulation potential for the lowest 1 kilometer of the atmosphere. So here's South Pole, here's North Pole, equator. Down here is the surface Up here is roughly 1 kilometer's altitude. This shows the galactic cosmic rays coming in and being shielded under present-day geomagnetic dipole conditions. If the magnetic dipole moment is zero and also the solar modulation potential is zero, it's an extreme case, not very realistic, but if we use slightly higher values here, not much is changing in that situation, then we lose the latitudinal dependence and we get the galactic cosmic rays making it down and producing ion pairs. I should say this is ion pair production in ion pairs per gram per second shown here. So this is the completely unshielded case. The difference is shown here. So the difference is most pronounced in the equatorial regions, ranging from 15% to something like 55% at 1 kilometer altitude. So taking a certain elevation into account, and the zonally averaged looks like this. So with increasing altitude, of course, the effect is obviously stronger, going close to 50%. Well, 55% also here over the magnetic equator. This is what the model results in. So model simulation results for boreal winter, nitrogen oxide anomaly in percent, showing a massive NOx production throughout the stratosphere and throughout the mesosphere, also going down into the troposphere. This is, of course, an unheard of response of the atmosphere. So a lot of NOx being produced by those energetic particles. At the same time, also a lot of HOX, OH and HO2 being produced. Now, the production rate increases very, very similar all over the globe as the NOx production rate. However, in concentration, this only plays a role in the winter hemisphere, where most of the HOX is in HO2, while in the southern hemisphere, the OH reacts very, very quickly with a lot of NOx that is there, and therefore even can make a negative anomaly here. Taking this effect and this effect together, they act on ozone. So there are NOx-induced ozone destruction cycles and HOX-induced ozone destruction cycles. And pretty much the entire lower and middle stratosphere, well, actually going up into the upper parts of the stratosphere, there's ozone loss, reaching something like up to 5%. And since here is most of the ozone layer, this basically also corresponds to 5% ozone column loss at the ground. This is again the same picture as on the slide before, showing ozone. Now we see what this means for temperature. Ozone leads to heating the stratosphere because ozone absorbs UV radiation. So if we reduce ozone, we get lower temperatures, as we see here. On the other hand, the winter lower stratosphere, polar stratosphere, is warming. So obviously the Boer-Dobson circulation, which pumps the air up in the tropics and then into the winter hemisphere, is strengthened. I will get back to this in a moment. So obviously the airflow here from the tropics deep into the stratosphere and mesosphere and then low down, coming down into the polar regions is strengthened. What that means is that you have compression heating here. So adiabatic heating, the air is compressed and therefore gets warm. Everywhere where colors are shown here, this is statistically significant on a 10% level. since there's less ozone here and temperatures are cooler, this means that the temperature gradient between the tropics and the polar regions is diminished. And this in turn means that the zonal winds are weakened. So the polar night jet is slowing under those conditions. What does it mean on the ground? Well, we have a high pressure over the Arctic, which you see here in the upper right plot. So hatching indicates statistical significance. We have a low pressure anomaly over Europe. So this shows the difference in surface pressures between the perturbed case and the reference case. So the case without magnetic field and the case, the reference case, which basically has nowadays magnetic fields, Earth and solar. Also, there are lower temperatures in Northern America, as you see down here, and higher temperatures in Europe, as you see here. Now, this structure with higher pressures over in the polar region and lower pressures over Europe, and then this periodic change in temperatures, cooler, warmer, cooler, warmer, corresponds to what meteorologists call the negative Arctic oscillation pattern. So the jet stream meanders more under these conditions, showing, giving glimpse of the perturbation, while in the positive phase of the Atlantic oscillation, there's less meandering of the jet stream. We see also wind speed anomalies here, and in particular a strengthening in Northern Europe. Now, this means that also more waves are emitted when the air has to cross the mountains here, and partly these waves can travel all the way into the stratosphere where they break, and they are responsible for the poor Dobson circulation, and probably also responsible for the enhancement of the poor Dobson circulation that we saw on the slide before. I mean, I'm coming to the end. So model simulations results again for boreal winter showing ozone. Now this is a very, very clear picture. It's basically statistically significant everywhere. This is again boreal winter. So most of the globe we have a reduction in ozone. There's a considerable increase in erythema UV radiation at the Earth's surface, following from that roughly something like 5%. How was that all received so far? Now, there have been a number of positive responses, but then there were also negative responses and also comments which we tried to respond to, and which may or may not appear in science. And very, very roughly speaking, most of these comments say, well, the climate modeling part is fine, also the chemistry done there, fine. The isotopic part of the work is fine, but coming to the conclusion that all this is happening, the Laurentide ice sheet growing, the glaciers in Chile growing, the Neanderthals dying, the megafaunal extinction in Australia, this goes too far. Let me give you one short taste of a moderate response. So this is what Anna Goldfield wrote in the Anthropologic magazine Sapiens, beginning of March 2021. She's an expert on Neanderthals, and she had her PhD work on that. So she asked the question, are atmospheric catastrophes the reason for the Neanderthals' extinction? The answer is complicated. Thanks to specimens available from fossil record, there are reasonably accurate reconstruction of Neanderthal body mass and daily energy expenditure. While doing research for my dissertation, I calculated the average daily calories a Neanderthal population would likely need relative to the same for Homo sapiens. The bottom line of these calculations is that it was simply more energetically costly to be a Neanderthal than it was to be a Homo sapiens. Models of these two populations put into the same environment suggested that in nearly every circumstance, over time, Homo sapiens would win out. The new article is fascinating, and it is entirely possible that disruption of the Earth's protected magnetic field may have added to an existing series of circumstances that were not in the Neanderthals' favor. But headlines trumpeting that a magnetic pole switch killed off our ancient relatives are vastly oversimplifying the tremendously complex system in which Neanderthals and our Homo sapiens ancestors lived. Well, I think this is a good comment. Let me summarize. 42,000 years ago, during the run-up to the last ice age, a major loss of Earth's magnetic field coincided with a grand solar minimum and a weak solar wind. This coincidence led to anomalously weak protection of Earth against galactic cosmic rays. The galactic cosmic ray flux at low latitudes increased by up to 35% at sea level and up to 50% at 1 kilometer altitude. Chemistry climate model simulations suggest enhancement of lower stratospheric NOx and HOX by up to 40%, leading to an average ozone loss of 5%. This in turn impacts the stratospheric and tropospheric circulation, giving rise to local droughts and glacial maxima in Australasia and in the Andes, and the rapid pronounced expansion of the Laurentide ice shield in North America. The concomitant evolutionary changes, humans, cave art, megafauna, give rise to a radical idea, namely that the magnetic field of Earth might be much more relevant in our evolution. However, it remains to be seen to what degree these concomitant changes are a coincidence or really a causal connection. And that's it from my side. Thank you very much, and I would now be ready for questions. Thank you.
Thank you very much, Professor Peter, for your excellent lecture and its presentation. Thank you very much. And I ask, have you anybody questions, please? Oh, Yuri Grigoriev, please. Switch your microphone.
Maybe he was only clapping, but maybe he also has a question. We will find out.
Yes, sorry, I was only clapping. Thank you very much for this.
But maybe you also have a question.
Yes. Pavel Kupriyanov, your hand, no?
I guess Timofey would like to ask a question.
You can indicate your desires by hand, please.
Yeah. So, yeah, I have a question about the impacts. So you have shown this loss of 5% in ozone, and we know that, I mean, that's the exposure, the additional exposure over the long period of time. But in principle, how dramatic is this, given that we have large seasonal variations of ozone, which are much larger than this 5%, and the species are always exposed to that. And second question is, besides ozone and the additional UV reaching the ground, there's also a direct increase of availability of energetic particles, right, at the ground. Would this also affect the fauna and the biosphere?
Thank you for your questions, Timofey. Yeah, the first question is very, very justified. 5% ozone loss. That is basically the ozone loss that we also have in modern times due to us emitting CFCs, chlorofluorocarbons. And when this paper was written in this respect, was myself also always quite skeptical. And I was, so to say, waiting for the moment when the reviewers at Science asked the same question and said, well, hold on a moment. You are claiming ozone is having such a strong effect. How can you really convince me of that? This never happened. We sailed through. Obviously, people liked this idea of the Adams event. Okay, you're absolutely right. This by itself, what we cannot expect is suddenly a civilization falling down from one day to the other. Nobody is expecting this anyway, right? So it's one part of the mosaic, possibly, which was feeding into this transition from the Neanderthals, for example, to Homo sapiens, and also adding to additional stress on the megafauna in Australia. This might well be. It's highly speculative. And so I would not say there's no effect. I would stick to the comment which I wrote to you, which I read to you by this lady criticizing us that we should not trumpet so loudly, but rather make a more silent point here. Yes, I would agree with that. Your second point is another good one, Timofey. You are asking basically, well, do we at all need the ozone calculation, or could we actually stick to Ilias model? So let's see, where did I have?
I think it's the next figure. There was the ionization rates in different simulations.
Oh, I already passed it. Huh?
Yeah.
Here.
This one, I think. Yep.
This one, yeah. I mean, in this band here at 1 kilometer altitude, a 55% increase in galactic cosmic ray radiation. Well, I have to be a bit careful because we did not look directly at the galactic cosmic ray flux. Rather, all we had available in this comparison, looking at the ion pair production rate, and this increased by 55%. So this means that galactic cosmic rays, which are capable of splitting an N2 molecule, which needs quite a bit of energy, increased by 55%. Ozone only decreased by 5%, and erythemal UV flux therefore also increased by roughly 5%. So it might well be that we concentrated on the wrong target and that we should much more concentrate on this here. If this is really behind that, we do not need a chemistry climate model. The chemistry climate model then in addition helps to see, well, what is this ozone change doing in terms of temperatures, pressures, winds, which is, of course, by itself interesting. And yes, let me point that out again. Our model does suggest that the Laurentide ice shield is growing because there is a lot of cooling here. Whether it also suggests that the Chile glaciers are growing is a question, but since the first of all, it's statistically not significant here, but then the fact that the southern Pacific gets a bit warmer, if anything, might transport more water and more precipitation to the glaciers. So the model has a lot in it, which might be interesting to indeed look at. But coming back to your original question, sorry for the long answer, I fully agree with you when asking that question, whether there aren't lower hanging fruit, which we should have also looked at. Thank you.
Thank you.
Excuse me, I have one simple question. I heard that there were about 5 climate crises in the foreseeable history. Why did this one catch your attention? Is it nearest, or maybe maybe I have missed anything?
Yeah, now I'm not a paleoclimatologist, and maybe someone else in the audience knows the answer better than I. I mean, major climate crises, of course, are typically when you have collisions with larger objects, right, which then lead to a lot of dust going into the atmosphere, and then to a global winter, which might lead to species going extinct. Yes, you are right. This is one of the youngest such crises, and probably the youngest. And that is also then what makes the fine detection of the carbon-14 signal in this tree so spectacular. Now, over those 1,700 years that this tree was living 40,000 years ago, we have really a tremendously high temporal resolution, right? You see literally each ring of each tree ring and can make the analysis of that. Adjusting this whole archive relative to others like the beryllium is more complicated. The further back in time you go, the more difficult it is to see clearly such effects. So in this sense, this paper has probably a lot of value to it. And yeah, I think it's the youngest crisis.
Thank you. Any more questions, please?
I should correct that immediately. There is one more question by Andre. But I should correct this immediately. The youngest crisis is, of course, the one we are presently in, and that's man-made. That's the youngest crisis.
Yes. Please, questions?
No? May I?
Yes, please.
Well, actually, I have three questions. One more technical, and two, let's say, on the prospects of this study. And the technical question is, I'm not an isotope man myself, but I read about it quite extensively, and I got an impression that C14 and beryllium-10 should run more or less in parallel in terms of production. And therefore, the question: why in your figure there is a parallelism of the two records just when you enter in La Chambre, but not when you are leaving La Chambre?
Good question.
So
I mean, that was your first
maximum,
question.
Up to the carbon maximum, you have more or less parallel.
Yeah, yeah.
But afterwards.
So here is the minimum in magnetic field and the maximum in
carbon.
Yeah. and we see clearly the dip here, but then here, when we go out again, this is not the case. I cannot answer this question. I don't know the answer.
No, the question is why the beryllium remains high after carbon goes down.
It's at the bottom, the black and the blue line at the bottom.
Yeah.
Why does this go down while these remain high?
So. So okay. Okay.
If you're absolutely right, if anything, it could have been the other way around, right?
We need to ask Kaiser to people.
Yeah.
And
no, I don't know. I don't know.
And let's say two other questions towards the prospects of this study. Would it be that difficult to run the model using the more realistic model for magnetic field, because zero magnetic field is, you are correct, it's not very realistic. And basically what we have is that more or less what we have for the reversal instances or excursional field is that the non-dipole part of the field is more pronounced with respect to dipole. And so that would produce a bit different configuration of the magnetosphere, obviously. So
yeah, there the answer
is that difficult, I think.
No.
If you take the existing model, then it might be different. And the third question, starting from your climatic model, what kind of measurable paleoclimate proxies we should look for when looking for this magnetic signal in the climatic records? What kind of parameters would change the most? Temperature, humidity, something else?
Yeah. So, for example, 018 or yeah. To the third question, I must disappoint you. I again don't know the answer. Probably there's somebody in the audience who knows the answer better. Your second question is, as you say yourself, an easy one, so I can answer the easy question. This was indeed an extreme case that we assumed because we wanted to see, is there any effect at all? We did perform in an earlier study cases where we had phi only something like 100 or 80, which is indeed close to the lowest observed solar modulation potential during solar inactive times. And an M, which is more like 1 × 10⁻²⁰ amps meter squared, which is also close to observed minima. The results are then, on the other hand, pretty similar to this extreme case. So making the difference between 8 and 1 is the major part. Going then down further to 0 is not so important. Going down from 800 to 80 is the major part. Going down another step down to 0 is again not so important. And therefore we left it showing this result. Now, related to this is, of course, another interesting question, namely, why 5 years ago, when we published the Suter et al. Paper, did we not find a similar result? Back then, we had in our abstract, the last sentence of the abstract, which I read only again yesterday, reads, it's unlikely that there are global climate consequences. The reason back then was that we did not compare with 800 megavolts, but with 400. And this is, of course, a major difference. So our reference date was a different one. That is point number one. Point number two, of course, the interest has grown significantly by discovering this tree. So this also spurred the revived interest in that. We had to struggle quite a bit making our model again work, which we used 5 years ago. So it was that also added to not doing those additional sensitivity studies that you are asking for. So your questions are well taken. And your third question, I honestly do not know. The main authors of the paper did a lot of other comparisons. They compared with 018 measurements in ice cores. They compared with the carbon 14 in how is that called? Those oh, my English is too bad. Tropfstein. What is Tropfstein in English? I don't know. Where the water drops down in caverns and forms the stalactites and stalagmites, right? So lots of this has been done and is in the online material of that paper.
Yeah. Thank you. Thank you.
Thank you. Any more questions, please?
I can ask another question.
Yes.
So in your study, you mostly consider the effect of galactic energetic particles, but the Earth will be also exposed to the solar energetic particles, protons and electrons. And I remember there was a plan also to calculate if there will be some extra protons, solar flares, and electrons from the sun. And did you have some more results in that direction?
No, I don't. As you actually know, Timofey, I think. No, it would be interesting to do these additional studies, absolutely. We did not change, as far as I understand, for those simulations. We changed the galactic cosmic rays, but we did not change the solar particles. And this is, of course, if you like, an inconsistency, because how can we say that the sun was weak when we, at the same time, do not change the solar particles? So we very, very much focused on the galactic particles, which make it down all the way into the upper troposphere and even further down.
Mm-hmm. Yeah, and then one of the replies to that lady's comment could be, well, first of all, her explanation of just calculating the energies or calories needed for Neanderthals and Cro-Magnons is also simple, right? So it's the same thing as you did. And another thing that during this long period of time, there could be a couple of strong flare events, and like from the work of Ilya Usoskin, we know that statistically strong events, they happen every several hundreds of years, and then a couple of those events directed towards Earth would probably already change the game for Neanderthals. So.
Yeah. A question, of course, is why does it change the game for the Neanderthals and then not also for Homo sapiens? So obviously Homo sapiens was clever enough to hide in the caverns when such things happened.
But isn't there also some info that the skin structure is kind of different, and that Homo sapiens simply were less sensitive to UV? Have you read something in that direction?
Well, our colleagues from Australia were speculating on that back then the Homo sapiens managed to develop the ochre color with which they painted their caverns, but also painted themselves with it. And a question, but I don't know what the answer to that is that this might have been an ancient sunscreen.
No.
If this is really the case, then they protected themselves like this. On the other hand, the dietary arguments by our commenter there made me really think. I think these are good points. I think we were leaning far out of the window with this paper.
Maybe Homo sapiens also developed clothes.
Maybe also that, yes.
They were just well dressed for that weather.
Yes.
Please, other questions?
Maybe I will ask question. Thomas, for how long you can observe ozone depletion?
Well, I would basically say for as long as the grand solar minimum lasts, and as long as the magnetic, as the low magnetic Earth field lasts. This determines how long it is. There's I think hardly any delay. Once you switch those things again back to normal, the atmosphere takes, I don't know, maybe maximum 10 years or so, maybe 20, but not longer, to re-establish its situation again. And so this would be immeasurably short on a paleo timescale.
Okay, thank you.
By the way, what do you think of warming at this time? Is it really caused by carbon dioxide or not? Maybe this is another climate fluctuation.
I don't know whether one understands those Greenland interstadials, those warming events, the Dansgaard-Oeschger events, very well. And I'm not a specialist on that. So I think these are climate variabilities that climate displayed back then. I do not think that these are related to CO2.
Yes, thank you. Please, other questions, please. If there are no questions, so please, thank you again, Professor Peter. Thank you very much for your excellent presentation and your answers on our questions. Thank you very much. And maybe you have some comments.
I enjoyed it very much, being here and giving this talk. I would also very much enjoy if really the collaboration with Irina and Ilya together with Eugene will work out soon. And if I become involved in their project, that would be great. And I would then very much look forward to seeing St. Petersburg.
Thank you very much.
Thank you. We will try.
Yes, let's try. Okay.
And you are welcome at another our seminars in the future. Yes, and
Okay.
And for all, I'd like to inform that the next our meeting will be in September. Good summer for all and all successes. Thank you very much and goodbye.
Thank you for organization.
До свидания.
Auf Wiedersehen.
Auf Wiedersehen.
Bye.